We've talked a lot lately about electric fields, and so I want to go over that again with you because it's relevant to the next thing we're going to. So, as you recall, an electric field starts at a positive charge and it radiates away from a positive charge. And you can think of an electric field as being these imaginary lines that are made by a test positive charge. And positives don't want to be next to positives, so they go away. And then negative charges, of course, electric fields go towards them, just like a tiny positive, like a proton would. The lines actually go toward the negative charge. Another kind of electric field that you can look at is a really common one that you have in batteries and that sort of thing. And it looks more like two plates. And so you have a negative plate up here, and then down here we'll make a little positive plate. Like that. And this is a really, really simple battery where you have positive charge on one side, negative charge on the other side, and basically you can do work because you have these charges. But let's look at the lines. So if we draw the lines, the electric field lines, of course they're going to go from positive to negative, just like that. And they should be fairly uniform. And you have this interesting thing that happens on the side where they do this. And we call that fringing. Now, if you put a particle, we'll make it a positive particle, and you put it close to the positive plate, it has a lot of energy built into it. Because you think about those particles being close to the plate means that they're going to shoot off towards the negative plate. So you have a situation here where you're going from right here where you have high potential energy to over here where you have low potential energy, because charges that are alike don't want to be close to each other, so you store up energy by pressing them next to each other. Now you can create the same situation with a negative charge, except the negative doesn't want to be close to the other negative plate, so that is where you have high potential energy. And then as it shoots down, it loses energy. And so that's where it's got low potential energy. And so it's a little more complicated than with gravity fields when you have electrical fields, because there's two different charges and things can happen multiple different ways. So you see how with electric fields we can show that we're storing energy. And we call store energy potential energy, just like we did first semester, except this time we have electric potential energy because it's due to these electric fields. Now, the concept sounds complicated, but actually it's really simple, because if you take a positive and another positive and you put them really close to each other, then you have really high potential energy, because they don't want to be next to each other. And the same is true for two negatives close to each other. Right? Very high potential energy. Now, if you have a negative and a positive right next to each other, well, that would be low potential energy, because that's where they want to be. There's no real energy stored there. But if you have a negative and a positive really far away, then that will be high potential energy. You pulled them apart, and they want to fly back together, kind of like pulling a rubber band apart. We can also look at these potential energies just in a simple field by itself. So let me draw an electrical field here. And this is what we call a uniform field, because the lines are all evenly spaced and everything. And so it may be something like 50 newtons per coulomb or something like that. Now, what about a little positive charge? How could we increase its potential energy? Well, think about it this way. You know that over here you have some kind of positive charge because your field lines are going away from it. And over here you have some kind of negative charge. Okay, so what we can do is we can figure out what's going to happen to our potential energy as we move it over here. Now, that's what the particle wants to do. That's what it naturally will do. So we'd call that low potential energy. Now, to try and press it back against this plate, that would be creating a high potential energy. It's very hard to do. Now, we could look at the negative particle and kind of make the same inferences about it. If we're taking the negative and moving it over here towards the positive, well, that wouldn't take a whole lot. That's low energy. But if we're taking this particle and pushing it against the negative side, then that would be high potential energy. Notice, if we move the positive particle over here in this area, then it's going to be positive against positive. So if we move the positive particle against the field, it increases its energy. If we move the negative particle with the field, it increases its potential energy. So you have to think about what a positive's doing and what a negative's doing in the fields. So when we talk about potential energy, electric potential energy, that brings us pretty quickly to potential difference. And it's kind of a strange concept, but it's the change in potential energy per unit charge. So how much energy did it take per coulomb to make something happen? And that's called voltage, which you're all familiar with. And voltages are measured in volts, of course, but that's also a joule per coulomb is a unit as well. And when we did electricity as water on that handout, the example was pretty neat. It was this idea that what if you had a giant tank full of water and it had a spigot coming out of it? And that spigot, of course, would be running water out of it very quickly. And the height of the water was like the voltage. Okay, so it's how much the water is trying to push out. Okay, kind of like the pressure. And if you had another tank that was the same height but a lot skinnier, the water would actually press out with the same pressure. Now, it wouldn't have as much water to come out, and it would have some different characteristics, but initially the water would come out the same pressure, and that's kind of like voltage. It's kind of like the pressure pushing each charge out. And we normally see it in the shape of something like this, which of course is a little battery, and we have a plus and minus on it. Maybe it says something like 9 volts. And that's how much this side and this side have energy in between them per charge. That's the voltage across the battery, how much pressure it has basically pushing across it. That doesn't mean that it's necessarily really powerful. For instance, your car battery is 12 volts. And then the Van de Graaff machine that we were shocking each other with the other day in class, that actually has thousands of volts. Now, what's the difference? Well, your car battery has a lot more charge in it, kind of like this big tank down here. And then the Van de Graaff would be like a really, really, really tall, skinny tank where it packs a lot of punch, but only for just a second. So that's the way voltage works. There's 2 equations we use for voltage, or we're going to use. And one is voltage equals work over charge. Okay, and so that's joules per coulomb, kind of like what we just talked about. The other one is voltage equals electric field times distance. How far did you move in the electric field? Now, don't think of voltage as being really some absolute. Voltage is the change, okay? So it's potential difference. It would be like, how much have you just gone up recently? So a lot of times you'll see this as the change in voltage. So maybe you started at 10 and you went to 20. Well, your change in voltage, of course, would be 10 volts. And that's usually how it works out in the problems. All right, speaking of problems, let's look at this one here. We have a particle moving 10 meters in the direction of a uniform field with a strength of 100 newtons per coulomb. Its electrical potential increases by 5 joules. That should be electrical potential energy. All right, there we go. What is the charge? What is the change in voltage, and what is the charge of the particle? Now, I'm looking at the last part of that. What's the charge of the particle? And let me show you something right here. It says that the particle moves 10 meters in the direction of the electric field. So we have this particle here, and it's moving in the direction of the field, and it's gaining energy. Okay, you know that these fields go from positive to negative. What kind of particle is going to gain energy by moving towards the negative? Well, that would be a negative particle, because as they move towards each other, they compress, right? They add energy to each other, and they want to fly apart later. All right, now, so we know it's going to be a negative charge, but the first thing we'll look at is what's the change in voltage? Well, let's look at everything we have. We have a distance equal to 10 meters. Let's see, we have electric field strength of 100 newtons per coulomb. And see right there we have voltage equals ED. Okay, which of course is going to be 1,000 Newton meters per coulomb, which is joules per coulomb. Okay, and that's going to be the same thing as saying 1,000 volts. Joules per coulomb, or Newton meters per coulomb, is the same thing as a volt. Okay, now it says what is the charge of the particle? So we can look at that one and say, okay, V equals W over Q to find the charge of the particle. Now we know V is 1,000, so we end up with 1,000 volts equals 5 joules over Q. Now when we solve that out, we end up with Q equals 0.005 coulombs. Okay, but we also found out up here that this was negative, so we end up with a negative 0.005 coulombs. And those are the answers to our first and second part of that problem.